Hi there. During this session I'm going to be talking about the kinetic model of an ideal gas. So let me expand on what that really means. Kinetic model, or kinetic theory as it's generally called, is a model which involves us thinking about moving particles which represent a gas. So this kinetic theory is really useful because it allows us to think about macroscopic behavior of an ideal gas and use microscopic behavior of its molecules to explain those things. So we try and put those two things together as a link between the macroscopic and the microscopic world. So let me just kind of give you an example of this. We can start off thinking about gas pressure. Okay. If we think about gas pressure at a macroscopic level, so pressure equals force divided by area. Happy with that. Force could be seen as rate of change in momentum, so therefore force equals change in momentum divided by the amount of time it takes. Okay. So this comes from the initial idea, the macroscopic idea, that pressure equals force times divided by area. Now, if we look at this microscopically, the pressure of a gas is caused by the rate of change in momentum of molecules as they impact the container walls. So as we can see, these molecules, they're hitting and bouncing around on the container, and that change in momentum provides the pressure of the gas which is inside. So hopefully you can see that there's pressure which can be measured at a macroscopic level, but at a microscopic level it's actually due to these particles bouncing around. Let's go a little bit further now. What I'm actually going to do is I'm going to think about the fact that for kinetic theory to exist, a number of postulates, a number of assumptions need to be made. It is imperative that you can remember some of these postulates. The IB curriculum decrees that you may be able to state some of the postulates of the assumptions of kinetic theory. So let me take you through them. Gas consists of tiny particles called atoms or molecules. That's fair enough. The total number of particles in the sample is very large. So we've got large number mathematics. It only really works at large numbers. The particles are in constant random motion. The range of the intermolecular force is small compared to the average separation. Okay, so this intermolecular forces becomes fairly irrelevant. Some more postulates. The size of the particles is relatively small compared to the distance between them. So that means that they're small particles compared to the gap, which fits with the idea about gases. Collisions of a short duration occur between particles on the walls of the container. Okay. So that means it's kind of almost instantaneous collision. Collisions are perfectly elastic, so that means that no energy is lost in this situation. It happens so quickly that no energy is transferred. Going further, no forces act between the particles except when they collide. Okay, so we don't need to worry about electromagnetic forces, for instance. Between collisions, the particles always move in straight lines, so it's random motion, but they're traveling in straight lines because there's no other forces causing them to change direction. And they all obey Newton's laws of motion, which is kind of inferred in the last statement. So those are some postulates. Now I'm going to try and link some things up, some ideas. Let's think about temperature and particles. Okay, so temperature can be considered to be a macroscopic measurement. Hopefully you're aware that at a microscopic level, when a gas is heated, its heat energy is transferred to the kinetic energy of the gas particles. Okay. So, as we probably already recognize, temperature is a measure of the average kinetic energy of the molecules of an ideal gas. So we're linking these things together. This is a direct link between temperature at a macroscopic level and how it's shown as the average kinetic energy of molecules at a microscopic level. There's a formula which relates to this. This is something you actually don't need to worry about for the IB diploma, but there's some interesting mathematics which can be done with this. I'm going to go through a few more links now, and actually I'm going to use the examples of the gas laws. to try and get you to think about these different terms. So I'm going to be building up what's known as the gas laws. So we'll start off with Charles's law. Charles's law states that the volume of a fixed mass of an ideal gas, just saying that's constant, held at a constant pressure is directly proportional to its absolute temperature. Now what we mean here is, if the pressure is constant, if I heat up a volume of gas or a certain amount of gas, it will expand, and that expansion allows it to maintain the constant pressure. So therefore we find out that volume divided by temperature equals constant when held at a constant pressure. Another thing, this is Gay-Lussac's law, and he recognized that pressure is proportional to temperature. Now here you need to think about what happens at a microscopic level. Well, what we're saying here is that if the temperature is 0, using Kelvin as a temperature scale, that means that the particles will have no kinetic energy. And if there's no kinetic energy, that means that there will be no collisions with the outside surface, and that means the pressure would be 0. So that relates to Gay-Lussac's law, and he recognizes that pressure is proportional to temperature. Boyle's law. Boyle's law looks at the relationship between pressure and volume, and it worked out that, again we're thinking about particles, Boyle's law thinks that if we maintain, or look at the relationship between pressure and volume at a constant temperature, so if we keep the temperature the same, what happens is that if we increase the volume, that means there's more space and it takes longer for the particles to get from one side to the other and collide with the outside. So increasing the volume would cause a decrease in pressure, and as the volume decreases, so if I push down and reduce the volume of the gas, that means that the particles would be colliding more often with the edges, so therefore there'd be an increased pressure. So here's the where we have an inverse square relationship here. Okay, so pressure is equal to a constant divided by the volume. So all I've done here is I've just kind of used the gas laws to give you some examples of how the macroscopic world can be explained by microscopic actions. And these microscopic actions are defined by what's known as the kinetic theory. I hope that has been useful for you.